All right, welcome to WASA Distance Education. This is MBF3C Grade 11 College Prep Math. I'm Pete, I'm your teacher, and welcome. This is the last class before the March break. So next week we will not have our classes for the 4 days. So all next week we're off, we're taking a break, and give you time to have a little rest, and then we'll come back into week 7, and so we'll only have 3 weeks to go when we come back after the break. So keeping that in mind, if you're thinking of starting your key questions, you're thinking of starting to send some work in, you certainly want to get that started. Now, I don't expect you to work over the break, but of course, if you wanted to, you certainly could. And you'll be able to contact me through my cell number. You text me. You can text a question to me on my cell phone. And if you send me a Facebook message, I'll still get it. It just might take me a little longer to get to you. Facebook doesn't make it easy to have a work Facebook type account. All right, but I won't be in the office next week. Okay, but you can still get through to me by texting, or you can always send me an email at my NNEC email number that you should have in your study guide. Okay, and yeah. So what we're going to do, because we're kind of in a bit of an awkward spot where we have one last class here, and I don't really want to start a new unit. So what I'm going to do is I'm just going to do a little compromise. I'm going to do a review of Unit 3, make sure that we touched all the bases, and then I'll give you kind of the short version of our introduction to Unit 4, the first lesson about data management. We're doing surveys and uh, uh, collecting data, sampling populations, things like that. Okay, and those are some really important skills for the job market, and for a lot of surprising number of different professions and trades use those. So we'll just get started with that. But it'll be, if you get it today, then when you come back on that first day of after the March break, then you'll be that much further ahead. Okay. So what we did yesterday, now that was a pre-recorded show, so that was on nets, which was just a bit of a sort of an add-on to the geometry, trigonometry class. Kind of, probably maybe doesn't really fit with trigonometry, but it was there. So we had a look at nets, and it just the idea is to take a three-dimensional shape and unfold it in such a way that it's flat, right? Or take a flat shape and, with creases in it, fold it up so that it turns into a three-dimensional shape. And really, um, if you go online and you do a search for nets, nets of geometric objects or something like that, you should be able to find lots and lots of them, and you'll find them for free. There are some places that want to charge you money for it, and I'll get a link on my Facebook account actually to show you where to find some of those, because it can be a lot of fun just to make them, make the different 3D objects out of a flat sheet of paper. And the ones you print out, it shows you where to fold them. And some of the better ones actually have glue flaps on the pieces so that you don't have to tape things edge to edge, but rather you put a little glue on the extra flap, and you tuck it under the adjacent edge, and it makes a really nice shape. So that's the nets. As far as the actual work goes, I went through it yesterday in the pre-recorded class, and there was a bit of a problem, I think, with one of the key questions, and hopefully I pointed it out, that this is on page 39 of your Unit 3, that this first question, they have an extra um, rectangle in the figure, and it doesn't belong there. You can't actually make a three-dimensional object out of it. So, but then I showed a couple of examples on how to how you can create it out of what's left when we get rid of that rectangle, uh, unnecessary one. Okay, so the material in the book is just a bit of an intro to it, but if you go online, you'll find lots of resources, and actually it's fun, the stuff that they have there. So you can take a look at that. All right. Well, what I'm going to do just go straight back to the beginning, and sort of see where we come here for our trigonometry unit. So the first thing we did was we looked at right triangles. Okay, and this is kind of an important idea because we've just sort of gone down the road a fair ways. It's important to remember that SOHCAHTOA only applies to right triangles. You got to have a right angle in a triangle. It has to not just look like a right angle, but it actually has to have a little box in the right angle. Because if it doesn't have a little box, then whoever drew it is not guaranteeing that that's a right angle. Okay, very hard to make the assumption that it is if it doesn't have the box. Okay, so we can use our SOHCAHTOA, which of course stands for the three different trig ratios that we use on right angles, the sine, right, which is the opposite divided by the hypotenuse. So the sine of a particular angle. Now, the other thing about right triangles is that the hypotenuse is always the longest side in the triangle, always, and it's always the side that's opposite the right angle symbol, the box. Okay, so if you were sitting on that little box and looking out over the triangle, the side you'd see across from you is always going to be the hypotenuse. But as far as the other two angles in the triangle are concerned, the right triangle, the opposite and adjacent will switch around. If you're down here at angle A, the adjacent side to you is the one that touches that angle that's not the hypotenuse. And the opposite side is the side that doesn't touch that angle at all. Okay, but if you go up to B, you'll notice that the adjacent side now, see, is the one that touches the B. Okay, and the opposite side is the one that doesn't touch the B at all. Okay, so that's how you keep them straight. Being able to identify those quickly is and accurately is important for working with SOHCAHTOA. Okay, once you get it down, you'll remember it, but it can be challenging, at first, especially the fact that they switch around. Okay, so we looked at the sine ratio, and then the nice thing about it is that the other two, the cos and the tan, really work the same way. So anything you can do with the sine, you can do. You do the same stuff with the cos and the tan. If you're missing a side, you can find a missing side. If you're missing an angle, very often you can find the missing angle. And depending on what you have. Now, one other little bit about the right triangle that we really should probably acknowledge here, because I don't think they say it anywhere in this text, because I guess they assume you already know that. But if you've been away from school for a while, or just maybe you just weren't there in that when they covered it. When we have a right triangle, we know that. Here, I'm just going to write this down here. When we have a right triangle, all right, we know that this one's 90 degrees right here. We don't even, it's very unusual to see someone write that's 90 degrees because it's known to be 90 just because this right angle symbol is here. So if I have an A and a B here, okay, what I know then is, because, let's call that C, we know that A plus B plus C is equal to 180 degrees, correct? We know that. That's a fact. The sum of the interior angles of a triangle are 180 degrees. That's the way it's usually stated in a math textbook, right? The sum of the interior angles is what they call it. But what they're saying is the angles, if you add them all up, there's only three of them, you add them all up, it's going to be 180 degrees, always. Well, if we know a little bit about geometry, right? Or yeah, we do. We know a little bit about algebra, and so we can put our algebra knowledge to good use, because the C in this case is 90 degrees. So for a right triangle, we can say the following is true. So A plus B is equal to 90 degrees, you see? So we know that the sum of A and B are 90 degrees, which means that if you have one of those two angles, you can easily find out the other one. Okay, now, so you may get a question where, it may seem like they're asking you for something that you can't get, right? Because you're missing the angle that you need. But this isn't your kryptonite because that's the cosine law. But this is pretty close. I don't know. Someone can tell me what something a little below kryptonite is. Anyway, so A plus B is 90 degrees. So the other two angles that are not the right angle in a triangle sum to 90 degrees always. Okay, so you can put that to good use as you're working through some of these geometry questions. Okay, there's a few other things that you may pick up, right? Where if a line cuts through a parallel line, then these angles are going to be the same, and we use two lines, and those angles are going to be the same. There's a few like that. Also, the opposite angles are going to be the same. So it might be useful to go on to mathisfun.com. Mathisfun.com. It's a completely free site, and the reason I like it, okay, I printed everything except the H. Um, the reason I like our website, besides the fact that it's free, is that the material is really well written. It's written in a way that's very you can follow it quite easily, but it's not just for kids. It's for everybody. Okay, it's because they think that parents will use it, or people who are like trying to take their high school math classes and want to get a refresh. So they know that it's not just kids that are using it. So they write it in such a way that it'll be useful and readable for everybody. So you can go there and you can look at on geometry. You can look on properties of lines, parallel lines, things like that. If you want to refresh your memory on some of these things, that'll help you out. Okay. So we got that. So we studied the right triangles. We learned about SOHCAHTOA, which is just a way to remember what what the ratios are, right? And the first letter of each syllable in SOHCAHTOA is to assign the cosine the tan, and then the other two letters are the sides, opposite, hypotenuse, adjacent, hypotenuse, or opposite over adjacent. Okay, so it's very common to walk into a math exam and in high school and find everyone's got SOHCAHTOA written in the top right-hand corner, right? You might think that's everybody's name, right? Because everyone writes SOHCAHTOA there. But they just don't want to forget when they get nervous. Okay. Okay. So we got the cosine ratio, and then the tangent ratio. And I pointed out here, just in case we missed it, that the on page 12 of the textbook, they made a mistake in this diagram. They were trying to illustrate the tangent ratio, and for whatever reason, they pointed at the hypotenuse. In fact, it's the tangent ratio is opposite over adjacent. That's the TOA in SOHCAHTOA. Okay, and so that one's helpful for you when you have when you need an angle and you have an opposite and an adjacent, or if you need an opposite and adjacent. And the nice thing about that, the tangent ratio, is that once you get your opposite and adjacent, you can use the tangent ratio for it perhaps. But once you get your opposite and adjacent, remember that the square of the hypotenuse is equal to the sum of the squares of the adjacent um, and the opposite. Okay, that's your Pythagorean theorem, right? A squared equals b squared plus c squared, or however they put it. But what it means is that the square of the length of the hypotenuse is equal to the sum of the squares of the other two. Now you'll notice that this looks quite a bit like the law of cosines, and it is because when we're dealing with a 90-degree angle, that the cos of 90 degrees, well, you can check it, but it becomes zero basically is what so that whole term, that minus 2ab cos whatever becomes 0. And so we're just left with this. So the Pythagorean theorem is what we call in mathematics a special case of the law of cosines. Okay. So, and so what you did in this first lesson then was you went through and identified all the different sides, the different ratios, and then you practiced on finding things. The only thing that they really didn't do was give you a bunch of questions and then kind of make you guess which one or work out which one to use, which ratio. They kind of, it was pretty clear, I think, just about all the way through which one you should use for most of these. So that's where, maybe a few more questions would be kind of helpful. You can go to Math is Fun or something like that. And then they asked a question about SOHCAHTOA. I don't think they really mentioned it all that much in the unit. But make sure you answer that if you're going through the key questions, because it's worth a couple of marks. I don't think they even put the marks on here, but usually a word question is worth 2 or 3 marks. So it's useful to try and answer stuff like that. Okay, write something down. I'm not that, as long as you communicate to me, right, then you'll get the marks. Okay, so don't worry about your grammar and stuff like that too much anyway. All right, so the next one that we went on to then is we learned about the sine law. Now the sine law is very handy because it's just as easy to use, I think, as the SOHCAHTOA, right, as the trig ratios, because all you need is a couple of sides and an angle, or a couple of angles and a side, and then you can start kind of peeling back the other information about the triangle, because you can find the missing piece in there. And then once you have that, then you can use that ratio to find the third side and the third angle. So the sine law is just the sine of an angle divided by the length of the side opposite that angle. Okay, and all you need are 2 of them. It's expressed as 3 equalities, or 3 ratios that are equal, which is true, but you only need 2 of those, any 2, to solve it. And you actually only need 3 of the 4 pieces of information, right? So for example, if you were working out sine A and sine C over here, if you didn't know C, you could still find it from, as long as you had those other 3 pieces of info. Now the other thing we found out there is that when we have a ratio in mathematics, 2 ratios that are equal, it's also true that the reciprocal of those 2 ratios will be equal. Okay, now this may be sort of a strange concept, but let's try this. Let's say we have a ratio that's 5/10, and now we're going to think of another ratio that would be the same, right? Well, maybe the other ratio would be 4 over, let's see, is that it? No, 4/45. Oh, sorry, 20 over 40. Okay, I'm gonna erase here. Try. Ah, it does that every once in a while. I haven't quite worked out how this thing works yet. So let's say, yeah, it's still doing it. Okay, sometimes it works and sometimes it doesn't. Okay. Okay. I'm gonna try it one more time. So, well, 20 over 40. Yeah, there we go. Okay, so those 2 ratios are equivalent, right? If I do 5/10, 5 divided by 10 on my calculator, I get 0.5. And if I did 20 divided by 40, I'd also get 0.5, correct? Okay, so what the equal sign says is that one side is equal to the other. But what it doesn't say is that it doesn't say anything about the value, right, that's on either side of the equal sign. It only says that the things are equal. So let's try taking a reciprocal of both sides of this thing, right? We have 10/5 equals 40/20. Right? And if we work those out, what we have here is 2 equals 2, which is true, isn't it? If we work the one above, we have 0.5 or 1/2, right, equals a half. That's also true. Okay? So that's why we can use the law of signs, and we can put the signs on top or on the bottom across the equal sign as long as we're consistent. We put all the signs on the top, all the sides on the bottom, or vice versa. Okay, and it's because of this property that if you take the reciprocal of both sides across an equal sign, you're allowed to do that. It's the same as multiplying both sides by a constant, by 2, by taking the square root of both sides. There's a lot of things you can do on two sides of an equal sign, okay, that maintain the equality of the, right? So, if you think of a balance, like a skit, one of these beam balances where you have a pan on both sides, right? And if you put a quarter on one side and a quarter on the other side, right, it's going to balance. You put, right, if you put a dollar on one side, you put a dollar to a loonie on the other side, it'll still balance, right? Now, then if you go and you get a carburetor and you put it on one side, okay, even though that's a little unconventional, right? And you get another carburetor and put it on the other side, as long as the two carburetors are the same, it's going to balance, right? And that's the thing, and that's what this is all about. Okay, so it doesn't really matter as long as you do the same thing to both sides. You can do it, and that's how we make use of the sine law. All right. Now, then the next thing we did, okay, we spent a lot of time learning how to use the sine law in different ways, but there were some cases where we just couldn't use the sine law, and one of the most common ones that comes up is when we have three sides of a triangle and we don't know any of the angles. We want to know the angles, right? So then we have to break out the law of cosines. There's a couple other ones that can't be worked out by the law of sines as well. It's when you have sort of an awkward, you only have one angle and you have a couple of sides, but they're the wrong sides. That's how the law of cosines also doesn't work. It's because if you have two angles, you can still use that sum of the interior angles, sum to 180, right? So if you have two angles, you probably won't be using the law of cosines because you can always find that third angle and then use the law of sines. To me, doing a bit of subtraction and a bit of division using the law of cosine, using the law of sines, I think is easier than bringing out the kryptonite, right? It requires special handling. It's got squares in it. You got to manipulate things sometimes, and so it's the sort of thing you want to save for when it's really necessary. Okay, so it does a lot of stuff, but it's every time you use a more complex formula than you have to, you're taking a chance, right? You might make a mistake. Now, having said that, the other thing about the law of cosines is that they give you different variations of it, and because they give you the three different variations of the law of cosine. Okay, that's on page 27 in Unit 3. But if you think about it, there's also three different variations where it starts out as the cosine of an angle, right? That's the one where we worked out what that would be. And so if you did it the way the text kind of lays it out, you'd have 6 different variations to memorize. So I don't like memorizing stuff. I think it's it's just very difficult, right? Especially, you're sitting there and you're playing your Xbox, you're memorizing the law of cosines, right? You're eating your dinner, you're memorizing the law of cosines, right? Maybe you're listening to music and memorizing the law of cosines, and then you gotta sit in the learning center and someone slaps down a scary looking test on you, and now maybe you're not going to remember the law of cosines, right? So what we want you to do then is to be able to derive it, right? To be able to look at the triangle and say, okay, it's basically, if I'm looking for a side, then it's the sum of the squares, the other two sides minus 2 times the lengths of those sides times the cosine of the angle opposite the side I'm looking for, right? If you memorize it that way, then you can always write out the exact law of cosine that fits your situation. Okay. Now, just to be clear, we do give you these formulas on the final exam in MBF3C. Okay. It's on the last page of the exam. I just kind of put it in there. So look for it during the exam. We'll give you all the formulas that I think you'll need. Okay. And during the review, we'll actually look at those. Okay. But as a general rule, it's just not a good idea to try and, if you don't have to, try not to memorize stuff. Try and be able to kind of figure it out. Now, the other thing that we were doing with the law of cosines was sometimes, and this is the example here from page 28. Let's take a look. Okay, so find angle A. So we're being asked to find angle A, and the problem with that is that all we have are the three sides. We don't have any other angles, so we're really stuck. We can't use the law of sines. It's not a 90-degree angle in there. It's not a right triangle. The reason we know that is because there's no right angle symbol in there anywhere. So we're really stuck. But we can use the law of cosines because we have three sides. The only thing we don't know is that angle. So we just change the format of it, and we start out with the standard one. Okay, so a squared equals b squared plus c squared. Little a squared we have, and it's the a that we don't have. That's the piece of information we don't have. But everything else we have. So now we're just basically using our powers of algebra to isolate cos A to get that by itself. Okay, so the first thing I did here, and the minus 1 actually came later, but the first thing I did was I moved the b squared plus c squared to the other side, and of course it flips the sign for each term. Each term it's tied into the one side with an addition or subtraction. When you move it across the equal sign, it flips the sign. Okay, so then we were left with some minus 2 BC cos A, and then what I did was just to kind of get things get the signs of everything worked out. I multiplied both sides by -1, which flips the sign on every single term on the left side, and it flips the sign of this one thing on the right side. And it's one thing because it's all multiplication. Okay, it's only, you only have to flip the signs when it's each terms, when you have a bunch of terms tied together by addition or subtraction. On the left side, it's one term, right? The term is 2bc cos A, right? On the left side, our terms were, negative a squared plus b squared plus c squared, three terms. So now what the text does for you, you can do this or not. They don't like having a negative sign as the first term in an expression, so they just move the a down to the end, right? And so then they kept everything that they kept the first term. It starts with a positive, right, a plus, and of course you don't show the plus sign. So, and that's just to make it look a little better, I guess. It makes sense. And then we didn't have to do anything on the other side. And then finally, the last thing we do is we isolate cos A by dividing both sides by 2bc, which just ends up being divided on the left side, and then it just gets rid of it on the right side. Now, remember, this is an equal sign, so if you wanted to rewrite this and say, cos A, cos A, I don't know what I'm doing here. Cos A equals b squared plus c squared minus a squared over 2bc. If you wanted to write it that way, you can write it that way, with the cos A, the unknown, on the left. It's a more conventional way of doing it. But let me assure you that mathematically both of these are the same. They mean the same thing. Okay. Now, there's a couple other things. Now that you've had a little practice, a little experience using the law of cosines, there's a few things I want to tell you about that will help you avoid mistakes or detect errors, right? one of the things that will help you is to understand that the number you feed to cos has to be a positive number. Okay, so that means that the numerator and denominator, um, if there's any, it basically they both have to be positive, basically, right? Which makes sense. You can't have a negative side length in the denominator. That's not possible, right? So the denominator has to be positive, right? You can't have negative 3 centimeters for b, right? It's going to be positive. So we know that that's going to be positive, which means that the only way to get a negative number up top here is if this term was bigger than those terms. Okay, let me tell you why that should not be possible, right? It shouldn't be possible, okay, if everything's correct. Okay, so if you get a negative number in the numerator of this, stop right there and go back and look. Maybe you got your sides mixed up, right? Or maybe you made some other error there somewhere. Okay, so that's, and this is sort of thing that, once you've been working with this law of cosines for a while, you'll get to sort of recognize that pattern. But definitely the top number of the numerator has to be positive. Otherwise, if you try and give a negative number to cos, actually the inverse cos function, it's going to set off an alarm or do whatever your calculator does when you feed it an invalid number. Okay, yeah, sine and cos are both have to be positive numbers. Now the other thing here is that, let's see, yeah, I think cos, and it should be a fraction, right? Cos should be less than 1. Okay, or maybe 1, the biggest, 0 to 1. You don't want to have it like a 5 in this ratio. It's not going to work. Okay. All right, now let's move on here. So, and if you have any questions, certainly welcome to call me. We will be in the office tomorrow morning, but apparently we're not going to be in the office tomorrow afternoon. So I guess that's the March break. But you're certainly welcome to call me. Friday's a good day because I don't teach on Fridays. Or you can send me an email, as I say. Okay. So I think we went through that. We went through quite a few of those. There were a few questions where they give you directions. Let's see if we can find that. Yeah. So something like this. Question 9. This is page 30. When they're talking about due east, or when they're talking about northwest or south, they're not talking about Kanye's baby there, right? They're talking about a direction. Okay. So if you think of the compass, it's north, south, and now how are we going to do it? East and west. And there's probably, if you don't have that down, you might want to either memorize it or, if your smartphone, most smartphones have a compass. Yeah, I'm just saying, right? You take out your compass, right? And you'll see that that's the organization of it, right? So if you think about the directions then, so north, right? If you're at a point, right, and you're going north, that means that you're basically, flying in that direction. Okay. So let's, for example, a plane leaves Hamilton, flies due east for 75 kilometers. So if this is Hamilton right here and you're flying due east, that's the direction you're going, right? If you're flying, another plane's flying north, it's going in that direction. And the one that they keep throwing in there is, it'll be going northeast, right? And northeast, so that halfway between north and east, they don't tell you, but basically that's a 45-degree angle relative to east, and it's a 45-degree angle relative to north as well, right? Now, sometimes they'll give you direction. They won't just say northeast. They'll say a certain number of degrees, right? Or maybe they'll say west 10 degrees south, right? And then what they mean is that that's 10 degrees. It's southwest but it's 10 degrees from due west. It's 10 degrees towards the south. Okay, and what they're meaning is basically it's a very fancy way of saying the angle of depression, right, going west is 10 degrees. Okay. All right, so those are little tips, because a lot of these questions they kind of have stuff like that. They don't really explain it in the text. They just figure that you know what a compass looks like, and that when they say northwest, that they're talking about 45 degrees north of west, not Kanye's little baby. Okay. And then we already worked through, we did it a couple times, we worked through ball diamonds, baseball diamonds, and again, they assume you know what a baseball diamond is, and basically, you know, the baseball diamond is a square, right, so all of the sides are the same length, okay, and the thing about the diamond then is that it is just turned 45 degrees. That's why they call it a diamond, but in fact it's a square that's just turned slightly. Okay, but you can assume this is your home plate here, and then your first base, your second base, and your third base, and you can assume that all the distances between all of those bases are the same. Then somewhere here, there's a pitcher's mound. That's where the pitcher stands, and you know, in there's different distances. There's probably some official thing, but there's different distances for it. And very often the questions will be, you know, how far is it to home, or how far does he have to throw it, or, you know, whatever. So this will give you an idea then of how you can tackle those problems, remembering that because this thing's a square, all of those angles are 90 degrees. Okay. Okay, well, it's kind of ugly, but anyway, so that's what it looks like. Okay, so that's what we're trying to kind of, when we're talking about ball diamonds, that's what we're talking about. And then golf, you know, they're talking about golf, and usually it's a tee. So when you're playing golf, you kind of stand in there, and you got a club. Sort of looks like a hockey stick, but it's got a small little thing on the end of it, and then you hit this ball from a tee. And it's called a tee because it's just literally a little peg, a little wooden peg that you stick in the ground. Looks like sort of a bit like a tee anyway. So the ball sits on it, you whack the ball, and then it flies somewhere. Now, if you do a top-down view of that, maybe the person standing here, right, and then they're aiming at this hole, and the hole, the way you can see the hole, it's got a flag sticking out of it, usually a pole with a flag. But the way it works is the hole's still big enough that if the ball goes towards the hole, it'll still fall in even with the flag in there. But what'll usually happen is this is the tee, right? And you want to hit it straight. You want to hit it straight, you know, maybe 200 meters or whatever that is. But and this is looking down. But very often what happens is the person's not very good at golf, and it just goes off to the side. And not only does it go off to the side by a certain angle, but the distance it goes isn't nearly long enough, right? Unless you're some pro golfer, it's usually got to take a couple, right? So you got to take a couple hits at it. So what you do then, you know, in golf is you walk, or you drive this little cart over to the ball, and then you hit it again towards the tee. And the idea is that you hit it a few times, and the more times you hit it, the higher your score is, which is actually in golf, it's actually a bad thing. It's supposed to get a low score in golf. Now, if you've ever played marbles, it's a lot like marbles, only you're not just pushing the little marbles around, you're whacking a ball. So that's golf. So very often what they'll say is something like, you know, the distance from the tee was 200 meters, and then he hit it 180 meters with an angle, you know, of 31 degrees. How far is it from the tee, you see? So, and that's probably a reasonable thing, because what he wants to do when he gets to the ball is he wants to know how long it is now. Because when a golfer's standing on the tee, there's some sign there saying it's 200 meters to the tee. Okay? But when he walks out into this field and finds his ball lying there, Now he doesn't really know how far it is to the tee, so he has to pick the right club to use to hit that ball. And so he'll want to know approximately how far the ball is away. And he picks a bigger club if it's long. He's got to hit it harder. Okay, so that's the way it works. There's a lot of questions about golf because there's a lot of geometry in there. It's a fun game. I played it before, but I usually have a very high score, which, as I pointed out, is actually bad in golf. As it turns out, it's bad. But it's still fun. You get to walk around. It's usually nice. Okay. So whenever you see golf questions, then hopefully you'll be all right. The other thing we talk about is rafters quite a bit, and those are the pieces of wood that are holding up your roof. And you've probably seen them before. You just didn't know maybe they were called rafters. Let's see if we can find one here in one of the questions. Well, maybe not. Okay. Anyway, so I'll make a new page. So when somebody's building a house, okay, and so they got the walls of the house, and let's try and make this a three-dimensional house. Okay, so now we want the roof to kind of have a point, right? So what they do is they put these rafters on, and they're spaced out every so often. And what that does is it gives the right, and then they got those rafters, and then they go and they put plywood between them on top, and then they go and put shingles on top of the plywood, maybe some tar paper, stuff like that, right? So these things here, these 2x4s or whatever size they are, they're rafters. Okay, and they're just pieces of wood, but the thing about them is that they're joined together at the top. They're just nailed together with a kind of a plate that joins them together. But very often they extend. If we look at an end view of the house, very often the rafters extend past it, right? So there's a little overhang. So it's not just the top of the house, right? That they cover, right? So in other words, if a child draws a house, they might draw the house to look like that, right? But rafters usually hang down a little bit. And what that does is it protects the walls from rain and from some of the elements, and it protects the people as they're walking in and out of the house from snow sliding off. It makes sure that the snow and rain slides away from the house. So those are called rafters. So very often in the geometry, they're going to ask you to calculate the lengths of rafters and things. One of the things that will help you is to understand that to be correct, the rafters have to be the same length. Right? No one's going to build unless well, they would tell you, but in a conventional roof, the both rafters, both sides of the triangle that forms a rafter is going to be the same lengths, right? Now you can walk around Sioux Lookout and find all sorts of roofs that are asymmetrical, right? A roof that looks like that. So, or maybe the angle is a little less severe, but still it's not symmetrical. But the questions that we work on here usually aren't like that, or if they are, they would tell you. Okay, but if they don't say anything, then you can usually assume that those are the same length. And remember that they will give you something like this distance right here, and I just didn't quite draw it as well as I could have. Okay, let's kind of, all right, well, that's all right. If I can get this. Oh, look at that, I got it to work. So, yeah, so those are the same length. So they'll very often they'll give you this distance right here. Let's just make that red. So that means that you can work out the length of this part of the rafter, but if there's a little extra left over, they'll tell you how long that is. And it's really up to you to add that length, right? So you'll work out how long this part, which I'm going to make as a dotted red line, you can work out how long that is by using your triangle formulas, but then you have to add that little extension, the part that hangs over your house. Okay. So you can imagine that this would be an important thing if you're gonna be a carpenter, if you're gonna be in the building trades or roofer, stuff like that. So you'll be doing all these calculations, working out what angle to make the the rafter, the join between the rafters. You'd be using pre-made rafters, but you might want to check it, right? Or there might be some custom work to do. All right. So I think we got everything that we're going to need as far as the all the extra stuff that they assume you know. One thing I want to talk about though, just as we're kind of getting ready to wrap this up, is the talk quite a bit about the 4-step problem solving model. Okay, I call it the model. Some places it's called the process. Okay, and if you go online and just type 4-step problem solving into Google, you'll find all sorts of resources about it. And it's just it's all pretty good, right? But they'll all often have a diagram or something, and I've yet to find a discussion of the 4-step problem solving model that has a diagram that really doesn't make it more complicated. Maybe if you find one, seriously, if you find one that seems to make more sense that has a diagram, then I'd appreciate it if you'd let me know. Because to me, the 4-step problem solving model is pretty simple, and then you get all these websites that give you like a 4-page diagram. So I don't know. Anyway, maybe it works. Okay, so the first step is understand the problem. It works in math, but it also works in a lot of other things. Let's say you go to start your truck, right, and it won't start. So you're going to call your uncle who knows a lot about trucks, call your aunt who knows a lot about trucks, and say, my truck won't start. And the first thing your aunt's going to say is, well, what kind of noise is it making? What's it doing? Is it not turning over? Is it making a click? Is it making a sort of does it sound like a cat is in there? So and that's the first step, is understanding the problem, trying to understand what might be causing the problem. Okay. So number 2, make a plan. Okay. So in math, by the way, understanding a problem, it might be something as simple as looking up what a rafter is, or if they're talking about a staircase in a geometry problem and they're saying the riser, the riser, and then you have to go look that up to see what a riser is and how it relates to your problem. Okay, so the second one is make a plan. That is figure out what formulas you're going to need, figure out how you're going to solve the problem, right? And that's just it's a plan, it's a preliminary plan, right? So maybe you call your aunt about the truck, and she says, make sure the battery's charged, right? So that's making a plan, right? You're gonna go, you plug the battery in with and you'll check, and then maybe it'll show that the battery is fully charged. So okay, so now we're still in step 2, right? But that was one piece of information. So we'll go, all right, we know the battery's good, so maybe we'll check the starter motor. We'll check that there's gas in it, whatever. Make a plan, right? And so step 3, okay, so in math, that's going to be coming up with the formulas we're going to use, have a diagram, look at the diagram, put all the information we know on it based on our understanding. Okay, and then 3 is just carry out the plan. Carry out the plan. Now, if we're trying to get our truck to start, and then we made a plan, we checked the battery, checked the starter motor, checked the fuel. Your auntie says you didn't try to start it with no fuel in there. Okay, and then 3, carry out the plan, is you're going to get the red jerry can from the shed. You're going to walk to the gas place, fill it up, right? In the case of math, you said, all right, I'm going to use the law of cosines. I got to find out a certain missing side. I'm going to find that missing side, right? And then I have to use that missing side. I'm going to use the law of sines to find a missing angle, right? That's carrying out the plan. And then you get to the end of that. That's usually the carrying out the plan is the easy part, even though that's the part that most math classes emphasize, right? Practice solving problems over and over and over again, right? That's what you're practicing there. But really, these are the things that really make you a valuable employee when you're out. They make you you bring skills to be able to solve problems, right? Carrying out the plan, very often someone that doesn't understand the problem can follow the steps, right? But coming up with the plan, someone has to really understand the problem. And then finally look back. And that's it, look back. Look back is something like you got to the gas bar as you were carrying out the plan with your jerry can, and they wanted some money for the gas, and you forgot to bring some money, right? Or you get to the gas bar thinking that they'd be able to lend you a can for the gas, and then they don't have a can. Somebody already borrowed theirs and didn't bring it back, right? So that's where you say, next time I'm going to do this differently, right? In mathematics, maybe you use the law of cosines and you look back and you go, I really could have used the law of sines for that one, right? Or you look back and you say, well, I don't really know what I got here. I guess I didn't understand the problem. And then you have to go back to step one, but it's usually quicker the second time around. Okay. Another thing I use the look back step for, very important in mathematics and a lot of things in life, is to say, does this make sense? Right? So if you're coming up with a rafter that's 1,500 meters long, okay, that's a pretty big rafter, and unless it's the Sky Dome or something, chances are something's gone wrong. Okay, so looking back is your way of sort of quality control, right? If you have a measurement for the side of a triangular pond that's negative 15 centimeters, chances are something's gone horribly wrong. Okay, but that's the fun thing about math, because you can go back, find out where you made the mistake, and just fix it all up, and nobody cares. Nobody cares that you made a mistake the first time you tried to solve the problem. Okay, just getting the answer. So that's what we use the look back step for. Okay, and I guess that's going to be it for today. We'll come back and we'll start Unit 4 on Monday when we come back. So make sure you have Unit 4, and hope you have a nice March break. Bye now.